we started the record. Okay, great. Yeah. Um, so um, yeah, thanks everyone for joining today's past seminar. It is great and our honor to host Dr. Minghao Shen as the speaker today. Dr. Minghao Shen is a member of the behavioral simulation team at Aurora Innovation. He received his PhD in mechanical engineering from University of Michigan in 2025, and his research focused on energy efficient, data-driven connected cruise control for connected and automated vehicles. At Aurora, his work is mainly on the core behavior simulation engines that test and validate autonomous trucking system before they hit the road. And his work spans realistic traffic scenarios, vehicle dynamics, actor behavior to ensure the Aurora driver performs safely across millions of miles of virtual driving. So let's welcome our speaker again, and the floor is yours.
Thank you, Professor Wu, for your kind introduction. Let me share my screen. I just want to make sure everybody can see my screen.
Yeah.
Okay. Yeah. Cool. So today, the title is From Theory to Highway. So essentially, the theory part belongs to my Michigan work, and the highway part belongs to the Aurora work. So just kindly briefly introduce myself. I'm recently graduated from the University of Michigan, and yeah, I will talk about my research in the connected cruise control, especially the energy efficient data-driven control for the connected automated vehicles. And on the second part of the talk, I will talk about what we are doing in Aurora. And this will be like in a higher level and does not involve that many theories. So before I start, I would like to thank my collaborators when I was doing my PhD in the University of Michigan. So Professor Gaboros is my advisor, and a lot of work collaborating with Professor Chaozhe He. He's currently in the University of Buffalo State University of New York, and Professor Tamash. He's now currently in the Wichita State University, and Professor Adlan Vahidi. He's currently in Clemson University. So now let's jump to the theory part. So here we are mainly talking about the autonomous trucking. So it has been shown that the truck may have the great potential to bring a lot of benefits in terms of economy and economics, and in terms of the energy. And it's very important because 70% of the U.S. freight are moved by truck. But we can see a lot of potentials. For instance, the hours of service limit, for the human driver, is only like 11 hours driving per day, and the trucks are idle like 60% of time. So when the trucks get autonomous, there's a lot of potential of the boost of efficiency. And from apart from the autonomy side, when I was in Michigan, I also work on the a connectivity side, so the intersection of the connectivity and automation. So the idea of the connectivity is that when the vehicles are equipped with those connectivity devices, vehicles can talk to each other. They can share the information of their velocity, position. Some of other research may they can share their perception. And currently, in this talk, we focus on this in a longitudinal driving scenario, where the vehicles can share their information about their position and velocity. Currently, the connectivity is still not widely available on the traffic. So we can see a lot of there's a long history of research in the connectivity. I know in the California past, there has been research since 1990s. where people talk about the platoons, talk about the connected adaptive cruise control. And but considering the current scenario where the connectivity is still limited, we propose something called connected cruise control, where we do not expect all the vehicles on the road are connected to each other, but we assume some of the vehicles are connected vehicles, but some other vehicles are not connected vehicles. So um, this limited connectivity can bring us some beyond line of sight information. And the question is, with this additional information, how the autonomous vehicles can utilize the information and the information, how that information benefits the vehicle in terms of safety and efficiency. Especially we are focused on the energy efficiency. And so before we talk about so when we talk about if energy, we first have to write down the equations and understand what kind of information energy we are talking about. So here we write down the longitudinal dynamics of the truck, and the truck can have the dynamics is nonlinear in the sense that we need to think about the rolling resistance as well as the air drags, and the main driving force is the torque from the wheel. It may uh, it may be accelerating or braking torque, and the torque itself can be very complicated. The torque can be saturated, especially for the trucks, because of the power limits and the braking limit. So it can be very complicated, and it can also be delayed. There can be also some delay in the powertrain system. So basically, when the controller sends a signal, and it may take a few, for instance, a few hundred milliseconds before the powertrain really executes this signal. So we model this into two terms. We compact the nonlinear dynamics in the F, and we deal with all the saturations and the delays in the second term. So so when we are designing the controller, we kind of want to focus on designing the acceleration. So we introduce the nonlinearity compensation, where we here instead of directly designing the U control input, uh, we we want to focus on the desired acceleration, and lastly, the energy consumption. We are essentially we want to focus on the kinematic information. So here we are essentially calculating the power of the torque. So when the truck is accelerating, we consider it consuming energy. But when we hit the brake, we currently we ignore we just think it's not consuming energy. But sometimes for different powertrains, actually, we can have different GX. Uh, for instance, we have there can be like energy recycling, so the GX may be different. So here, the only kinematic states are needed. And before we dive into the controller design, we kind of want to understand what is the scenario we are looking at, especially what kind of human driver behavior look like. So here is a trajectory we collected on the road. Actually, this experiment was conducted even before I joined the lab. So it was like 2018 when my lab have like eight vehicles driving in a chain on a public road, and we observed some of the braking acceleration pattern, and we recorded this speed trajectory for all the eight vehicles. So there are two information I want to highlight. So first information is that human drivers are string unstable, in the sense that So for the vehicle in the distance in the front, for instance, the vehicle brown vehicle hits the brake, the other vehicles will brake consequently, and each vehicle will brake harder and harder and harder. So this is string instability that is the first thing, and second thing is that we can clearly see the delays in the human reactions. So, um, so when the vehicle 8 hits a brake, it may take a few seconds before the vehicle 1 to hit the brake as well. So keeping these two in mind, we can start to design the controller. So first, we can start with a simple reactive controller, where we have two terms. The first term, the alpha term, basically decides the desirable velocity for the given the headway. So basically, when the vehicle is close to the front vehicle, we want to drive slowly. But when the distance is far away, we can drive freely. And on the second term is the synchronization of the velocities. So the idea is that when we see the brown vehicle hits a brake, um, we kind of we kind of know that the red vehicle will also brake a few seconds later, right? And so with this knowledge, we can brake earlier in order to avoid the sudden brakes. And there's something that's actually counterintuitive. I would like to highlight is that in the controller, we introduce the additional delay to the feedback loop. So the additional delay means that when we see the brown vehicle hits a brake, we do not want to immediately hit the brake, uh, but instead we know that the red vehicle will take a few seconds, like before the red vehicle to brake. So we deliberately delay our reaction to the brown vehicle. So the question is how much delay we want to have in the controller. So the parameters we can optimize are the beta and the additional delay we introduce. So because of the delay, actually the problem becomes very complicated. Like how to relate the parameters, the beta and the sigma to the energy consumption. So the way we solve this problem is we consider the scenario in a stochastic system. So consider the now we are considering the system in the closed loop system. The inputs are the velocities of different vehicles we are connected with, and the output is the velocity of the ego vehicle. So we can even linearize the closed loop system and write down the transfer functions. And so when we consider it in a linear level, there's something called spectral theory. We can spectral analysis we can do. So now we consider the inputs, basically the speed of the other vehicles are stochastic, and especially we consider them as stationary. Why sense stationary process? And when it's also Gauss process and differentiable, we can actually prove that the average energy consumption of the ego vehicle is proportional to the standard deviation of the acceleration of the ego vehicle. And and then using the spectral theory, we can actually connect the average energy consumption to the parameters of the controllers. So basically, we want to optimize this giant objective function, and the parameters are hidden inside these transfer functions. And I would like to skip some of the technical details on how we do the optimization, but basically we discretize the uh, integration into summations, and then we apply some of the um, spectral estimators to estimate this term from data, the cross-spectral density from data, and then we apply. So this becomes a general nonlinear optimization problem, and we apply interior point methods to find the optimal parameters. But let's look at some results. And so here we consider two kind of simulations. On the top, the trajectories are look more smooth. It is the linear simulation. Basically means we ignore those power saturations. We ignore those nonlinear effects in the longitudinal dynamics. And on the lower side, we take all this physics into account into the simulation, and we can compare the. So we know that we can fix the velocity of the vehicle 1 and vehicle L, and we can compare the trajectories of different controllers like ACC, which basically we do not. There's no connectivity, and we can see a lot of variations in the velocity that definitely consumes a lot of energy. And with the connectivity, we can achieve a much smoother trajectories. And in the we can see with introduction of the connectivity, it immediately introduced 16% of the energy consumption. And when we take into consideration the delays, additional delays, we can have additional like 2% of the energy consumption reduction. Um, and there's something interesting is that we essentially we do not really know which vehicle we are connected to. We may in the traffic mixed traffic with sparse connectivity, we may be connecting to vehicle 8, we may be connecting to vehicle 2, and we can show that our method can find a good delays in for any kind of is ignorant of what vehicles we are connected to, and yeah, so here is the reactive controllers. And the next question is, what about the MPC? So in the MPC, there's a predictive controller. It has the advantage of we can consider multiple objectives and the multiple constraints altogether in the controllers. And in the MPC, the key problem becomes how we predict the speed of the vehicle 1, right? Um, so when we are driving the mixed traffic with sparse connectivity, the challenge becomes we do not really know what's happening in the middle, right? So we can detect the vehicle 1 using a radar, and we can connect to the vehicle L using V2X using connectivity. But what about what's happening in the middle? There's no how many vehicles are driving between, and what are the states of the each hidden vehicle? There are a lot of uncertainties, and it turns out that we do not really need to know every details, and we only need to think like worry about the input and outputs, and we basically consider the hidden vehicles as a black box. Now we are considering the dynamics of the head-to-tail dynamics. So the input is the vehicle the speed of the vehicle L, which is the vehicle in the distance, and the output will be the speed of the vehicle 1, the vehicle immediately in front of the ego vehicle, and we want to like find the dynamic system for the we want to find the head-to-tail dynamics from the data we observe. So here becomes a more abstract point of view. Since we are focused on the input and outputs, question is we can have the abstract model like on the left hand side. So this we consider the system it can be a linear system for simplicity, and we have a data set. Basically, we keep collecting the data of the speed trajectory of the vehicle in the distance as well as the vehicle one in the front, and we keep collecting the data. We would want to learn what is the dynamics um, of the system, and the goal of the of our MPC for the MPC purpose is we we are given the initial conditions like the input in the past few seconds, and we kind of want to know what is the output in the next few seconds. So with this and then we can feed our predicted YF into the MPC as the prediction of the behavior of the vehicle in the front. So the idea is that we have the Williams fundamental lemma is dealing with this. It kind of ignores what's happening in terms of the X, the state, but it focuses on the behavior of a system in the input and output level. And using the this lemma, we can formalize the optimization problem like this. So essentially, we can organize the data set of the U and Y data set into this Hankel matrix, and and we can after that we feel we can solve this optimization, which is essentially a linear least squares problem to get an estimation of the future output. And we can and because the input is the velocity of the vehicle L, the remote vehicle, we also have little idea about what is their future behavior. We can also do some of the autoregressive estimators. So combining this together, we get an estimation of the YF. And another good news is that although the least squares problem can be expensive to solve because the data when the data is when we keep collecting the data, the matrix becomes wider and wider, so it becomes harder and harder to solve the optimization directly. But we can use recursive least squares to like recursively update these parameters, so that these predictions can be very fast. So let's jump into the results, like the prediction accuracy, and we are comparing the predictions for the multiple methods. For instance, the IDM method basic means that we have an IDM model, and we really want to build the we really want to like estimate what's exactly how many vehicles are driving in between, and we want to estimate the state of each of the hidden vehicle. So which this is this method can be very expensive, and the result can also is very bad compared to our like input out like head to tail dynamics estimators. So um, and when we so here's something we can something interesting is that we have there's a plateau of the standard deviations. So the plateau means that actually changes when with the ego vehicles connecting to different leading vehicles. So uh, it turns out that when we connect it to a vehicle that's farther away from the ego vehicle, it can help us in terms of the prediction accuracy. So what's happening here is that we have an intuitive new explanation is that um, we consider the position as being the shifted copy of the so each vehicle is a shifted copy of the of the vehicle in the front, so that we are given the we are when we are given the UP in terms of in the past TP past horizon, we want to estimate what the red the eagle as the red curve and it turns out when because of the shifted copy pattern, when we connect it to the vehicle that's farther away from the S1, we have more information about what's going to happen in terms of the inputs the inputs. So so that's why we can an increase, see an longer and longer plateau. Basically means that we have more and more information about the leading vehicle. So, and we can then compare the energy consumptions, like we can have like 10% of the safe, even compared to the predictive a model with IDM. And yeah, so here's a summary of, of the energy efficient cruise control. Basically, we about reactive controller. We talk about the predictive controller, and we show that the controllers have can save energy even with low penetration rate, and yeah, so that's kind of I will conclude my research in the University of Michigan here, and I will jump to the Aurora. And I will guarantee that there's no more equations or math in the following slides. So I will talk about Aurora. So um, let's just have a brief idea of what Aurora is doing, right? So Aurora in last year, 2025 April, we did the first commercial L4 truck launch on the U.S. highways. First is we are doing L4 autonomous trucking, and until like January this year, we have reached like a 250 kilometer 1,000 miles of zero um, without the human intervention. And our truck is now operating 24 hours a day and 7 days a week. And in terms of what our product is called Aurora Driver, which consists of three parts. So it consists of intelligent self-driving software and integrated self-driving hardware, as well as a scalable map and data service. So we are collaborating a lot with a lot of OEMs, and we are doing the freight delivery for many of the logistics companies, and we are still expanding our customers as well. Now let's dive into more technical like we first we the architecture of the Aurora software is still can be composed into several modules like localization, mapping, and perception, planning, control, and and we are the simulation. We want to do test the functionality of each module in the simulation. So the simulator will need to be able to test each individual module as well as the system as like end-to-end as end-to-end system. So uh, the why we need to do the simulation. The first reason is that we want to make sure our trucks are safe, and essentially we have like five different levels of five aspects of our safety. It's like proficient, fail-safe, continuously improving, resilient, and trustworthy. And essentially, this can be leveled down into many very detailed level. You can see there's it's essentially is a very large framework. So for the proficiency, there are a lot of aspects we want to investigate. We want to investigate to make sure our product is reliable enough, proficient enough. And this architecture can be uh, traceable to concrete evidences, including the test results, audits, and the peer reviews. So because of our very comprehensive safety requirements, we want to do extensive simulations. Uh, like, but the problem is that we want to the real world operation can be very expensive, and so that we want to test all the combinations of uh, like different scenarios we may we may see on it can be combination of different weathers, different traffic and the road geometry and sensor state. We can go on and on and on. And with the simulation, we can essentially efficiently uh, test our system at scale. And and also we want to make sure that each code change on the vehicle can go through the comprehensive testing to make sure it's safe and reliable. And the biggest problem we have in the simulation is the sim to real gap. And there are actually uh, two ways. So one way is the sim to real validation. So we want to focus on what is the fidelity of the simulation, and can we trust our simulation results? And the key is that the sim behavior have to match those on-road observations, and we can depending on our ODD operational design domain, we can essentially categorize the different scenarios into different confidence levels. For instance, the simulations can be within simulation capabilities or with uncertainty or outside of capability. So we will put different weights. We will put different weights on the different simulation results. And we also want to feedback the uncertainties to the risk assessment team. And on the other hand, we have the real to sim, which is we collect a lot of on-road logs, and we want to reproduce them in the simulators. So and apart from reproducing, we also want to generate a lot of variants of the logs from the logs, and they can generate sweep across different speeds and the weathers and behaviors, and so this is another direction is that how we can efficiently reproduce what we see on the real world to the in the simulator. So so another key problem we are having in this behavior simulation team is that we want to model the road users' behavior. And so the most common way we do it is the real world grounding. Basically, we based on the road log from the log, we generate a lot of variants, generate the simulation for the log for itself as well as the many variants. And we also are developing the reactive multi-agent tests. The simulated actors can respond to the AV's behavior, and that creates the cascading interactions. And this is very challenging because one of the reasons is that the sim to real gap, the human have never seen share a road with autonomous trucks before, and their reactions are extrapolated, not interpolated. So that means there can be a lot of uncertainties in the other vehicle behavior. So the problem of this reactive modeling is that we is still not sure how useful and how much attention we want to pay to the sim results in these simulations. So and uh, and yeah, so apart from the simulation, we Aurora also did some research on in terms of the energy efficiency and sustainability. And this is based on the published white paper on 2024. So it's essentially a lot of intersections between what I did in the Michigan. So uh, so first we can analyze like where does the truck energy go? And it turns out that a lot of energies are going to the like air drags and rolling resistance and the acceleration as well as elevation. And only 50 to 40 to 50 45% on-road efficiency. So especially on the highway speed, air drag dominates the useful energy budget. So we can think about like we have multiple ways to uh, improve the energy efficiency. So there's a plan that immediately after the business launch, we can do some optimizations like limiting the peak speed and reducing the idling. I will talk about it, what is idling later, and reducing the deadhead. And in the middle term, we can apply more techniques from the eco driving, and in the long term, we can have a more even more like deep optimization in terms of like powertrains and the vehicle optimizations. So uh, the energy efficiency can improvement can be decomposed into like two aspects. So first aspect is the per mile efficiency, which is related to the speed optimization as well as the eco driving, and especially well for the human drivers, many of the trucks human drivers truck drivers, they drive like 70 to 75 mile per hour, but a road driver like usually targets are like 65 mile per hour, which is I believe a lot of speed, which is the speed limit for a lot of highways. And this reduction of the target speed immediately introduced like 9 to 17% of the fuel reduction. And also we can apply ego driving techniques, like we can make our uh, speed trajectory more smooth, avoid those stops and goes, avoid sudden accelerations, and this can have another like 9% of the energy save fuel saving. And this is for the per mile efficiency, which applies to every single truck. But as an autonomous driving company, we are able to do the optimization in the broader level, in the system level efficiency. We can reduce the deadhead and the idling. So the problem is that with for the human drivers, the humans sometimes they need the when they after they reach the target, they have to go back to the origin, wait for the loads, and drive routing home. Driver will route home. And for the AV, we are able to like set very flexible start and end points, and we can optimize the dispatch of the trucks. And and this AV does not essentially does not really need those idlings. And utilizations and off-peak utilization is that the human driver the should not drive like 7 hours per 11-hour driving window. And but our AV basically can do 24 hours per day and 7 days per week. So this results in less. This basically means we need less trucks for the same freight volume, and that also contributes to the energy reduction. So combining these two factors, per mile optimization and the system level optimization, we can compare like a conservative, like a near-term levels, and as well as the ambitious, like a long-term goals. And yeah, so we are expected to like there's like still 32% of the energy saving potentials. So and yeah, so we are near the end of the talk, and I will talk about Aurora's the next step for the Aurora. And so after the business launch in the last April, actually we have expanded like 3 times route. Like initially we only drive between the Dallas and Houston, and now we are able to drive all the way to the Phoenix. And yeah, in the longer term, we are there are some like financial there are some like financial goals, and there are some like in the technical level uh, we are looking at expanding our ODD, for instance, to uh, support more scenarios like rain, heavy winds, and light snows. So and yes, and we are expanding. We are expected to expand to throughout the Sun Belt, and in the future, we can. There's a plan to like move northward, and yeah. So in the summary, I talk about the safety framework, and that's why we need a simulation to verify the system in a large scale. And we talk about the simulations, the behavioral simulation, the sim to real gap, and the real to sim challenges. And we also talk about the energy efficiency. And we also talk about the our plan for the even delivering an auto truck in a larger scale. So yeah, and that's it for my presentation. And yeah, luckily I got it in time. So yeah, now it's time to yeah, I'm open to any questions if you have.
Thanks for the wonderful talk. Yeah. And I won't be able to see everyone raising hand in the room, so feel free to just directly ask if you have any questions from the audience in the room. Yes, please.
Hi, Minghao. Thank you so much for your great talk. And I do have like really curious about like your team in terms of behavioral like simulation. Can you actually elaborate more about like how you define the behavior here? Are you trying to model like the car itself or model like pedestrian? But I remember during your slides you mentioned that like in your simulation it's very rare to kind of include in the pedestrians.
Mhm. Yeah, we'll definitely include. So we will definitely include pedestrians. So let's go back to this architecture. So how the simulator work is that we want to be able to independently test each independent module, as well as we want to do the test for the whole end-to-end system. And for the behavior specifically, uh, it turn so for instance, in terms of the planning, the behavior will include the behavior of pedestrians as well as the other vehicles. And when you talk about the like vehicle the dynamics of the vehicles, there's we have a dedicated team to focus on the control the simulations for the controls. We really have a very detailed modeling of the all the vehicle dynamics. And does that make answer your question?
Yeah, and I also noticed that you have a like slides in terms of like sim to real and real to sim.
Yep.
So does it mean that it's similar to a digital twin like, so I guess it's still related to the behavioral question, like Are you trying to build like a digital twin for your like company to use?
Yeah, so I'm always curious, like, what is the definition of the digital twin? So maybe we are just having different names for for similar things. But so I would like so the idea of sim to real and real to sim is something that we want to make sure that when the system passes the test in the simulation, we want to make sure the system will be safe on the road. And on the other hand, when we see there's a accident, there's a like a takeover, like a human intervention in the real world, we want to exactly reproduce them in the simulator, and we want to be able to debug what's going wrong in the simulator.
Got it.
Yeah.
So basically, real to sim kind of referring to, because your cars is already on the road, they keep collecting data and all the like computer vision and all the videos, so it will
Mhm.
feed back to the platform that you built
Mhm.
to further enhance it.
Yeah,
Is that
we can. Yeah, essentially we can like even reconstruct those scenarios from the sensor data. Yeah.
got it? Thank you.
Yeah,
I
I
have a
have a
go
go
ahead.
ahead, Scott.
Okay. Minghao, do you mind going back to the slide where you had the perception planning control diagram?
Yep.
Okay, so it seems to me that so I have a question ultimately about safety, but I'll wind up to it. So, it seems to me that the industry has moved from AV 1.0 software, where it's modular in the way that you describe on this slide, to AV 2.0, where it's end to end in the sense that there may not be separated modules that are doing the perception planning and control that you could like interrogate if you want some transparency or you want to do some validation. Okay, I won't ask details on the software strategy, but I'm curious for the safety case framework, which is, of utmost importance. Uh, is the way that the safety case frameworks being defined such that it prevents AV 2.0 software and end-to-end framework? Can you talk about that interplay? Like, can you do end-to-end perception to control and still be able to come up with a safety case framework?
Yeah, that's a good question, a very good question. So, um, yeah, so what's good about the current modular design is that we are really be able to trace back all the way back from the any failures back to we can do the triage that what module goes wrong. But for the end to end, it seems very difficult, and it becomes more like a black box level. So at the so essentially, I think if you look at those definitions of the proficient, um, all these terms, um, they is still, I believe, is still an open question how we can really build a framework, or on the other hand, I think it's always this framework can be a good guidance for us to build our test data set, right? So I believe even for the end-to-end driving, we it's more like we want to be able to like reliably evaluate the capabilities of the system by by testing it on diverse enough testing data. So so I think starting from this framework, it may be a good guideline to design what is a good benchmark for the system. So does that answer your question?
Yeah, I think, well, your answer, of course, I think it's important that it's not like there's any US regulation on what these safety frameworks are, right? This is, private industry self-regulating itself. I mean, maybe there's some level of consensus that's happening across the industry, but I think what I'm getting from you is this is a starting point, and as the software architecture evolves, maybe we don't have to start this framework from scratch, right? We can,
Yeah.
yeah, okay. Okay, I think that's what I'm getting. All right, I
Yeah,
have to jump. Let's see.
I have a question related to what Scott asked. So, um, like how do you tell that like one like either each level of the safety is reached? Like I understand that you would collect the actual driving data and you analyze them, but where to draw the line to say that okay, so this is enough testing, we're confident that a certain level of safety is reached.
Uh, yeah. So I believe this kind of this is a guideline for us to design what is our like test
Mm-hmm.
test benchmarks. Uh, and if you look down to for instance, we can look at a fail-safe, and
Mm-hmm.
we can go all the way down. And it can be very concrete requirements like the frequency of like
Mm-hmm.
yeah, minimal risk maneuvers is sufficiently low, and
Mm-hmm.
self-driving system are designed to robustly operate in their intended ODD. And yeah, these are just like criterias, and this just sets a bunch of um, criterias for before our software release. Like
Mm-hmm.
we have to pass all these tests.
Yeah, so I guess my question was more on the size of the data set. Like if you, when you do only a small amount of driving test, you wouldn't, for example, observe that many of maneuver, right? So like
Mhm.
you also need to not only assess whether the metric is reached, but also the confidence interval of such metric,
Yeah.
Mhm. Yeah,
right?
definitely. So
So you may not know the underlying distribution of such an event. What you observe is a sampled realization from the test, but there is no way to really know what's the underlying distribution,
yeah,
right?
exactly. Yeah, I agree. And mm, yeah, I cannot comment too much about like whether that method is scientific enough, but
Mm-hmm.
I would say the data is definitely the key to the autonomous driving. So that's why we want to expand. And of course, and actually, and in fact, we when we expand to other states from Dallas to Phoenix, actually we
Mm-hmm.
find many things are different,
Mm,
many different things. Like we can see some of the algorithms are not good enough. So
mm,
we keep having this findings when we move to a new place. So
I see.
definitely data coverage, yeah, is
So
definitely important.
what mainly changes when you change a city? Like is it the road structure, the lane, the kind of the width of lanes that change or people's behavior change?
Um, so yeah, so Aurora many were most of the time Aurora drives on the highway, right?
Mm,
So in the in a big so what I'm referring to is many for instance, there are some randomly the sometimes there are some objects on the highway that that's not expected. Maybe a tire,
mm,
maybe an animal, maybe
mm,
something else, and the truck have to be able to deal with them. So when
yeah,
we move to other places, so this is something that can be very different in different places.
I see, I see. Okay, that makes sense. Yeah. Okay. Are there other questions from the audience? Okay, if not, then let's thank our speaker again. Thank you very much for the wonderful talk.
Thank you for the invitation and
Thanks.
for all
Thanks.
the questions.
Yeah, we hope to host you maybe one day in person when you get a chance to come to Berkeley.
Yeah, definitely.